In this section, we're going to look at what happens when you heat things. And so we're going to start out by looking at heat transfer and the concept of specific heat capacity, which we'll explain when we get there. Then we're going to look at how you can calculate temperature changes. That is, if you're heating something, how much will the temperature change by? Then we'll look at changes of state when things melt or boil or freeze or condense, and how that is associated with amounts of heat being transferred. And then finally, we'll put all of it together with heating curves. So the first thing we're going to do is talk about what happens when you do heat something. When you take something and you heat it up, you add heat to it, thermal energy to it, what happens? There are really three possibilities. One is the thing you're heating gets warm. That's the thing you're most familiar with. The second thing is a change of state can occur. And you're mostly used to that in the case of water, where you take ice and melt it. So you add heat to ice and it turns to liquid water, and you add heat to liquid water and it boils and turns to steam, which is gaseous water. The third thing that can happen to heat energy is it can be used to drive an endothermic reaction. That is, an endothermic reaction a chemical reaction can absorb that heat while it occurs, while the reaction occurs. So we're going to go over the first two of these first, and we'll be doing the third one in a later section of this chapter. So first, let's look at how much heat is added to a substance and what happens to the temperature when you do that. And to do that, we're going to use a little simulation, which I don't have right here, but will shortly. So if you take for example, a wood block at 20 degrees and you heat it for 3 seconds with a Bunsen burner, about 150 joules are added, and when you add that 150 joules, the temperature of the block goes from 20 degrees to 37 degrees. So it goes up by 17 degrees when you take a 5-gram block and you heat it with 150 joules. Let's instead say we have a piece of glass that's 5 grams, same mass of substance, but a different substance, and we'll heat it for the same amount, 150 joules, that is 3 seconds. And now it goes up a lot. The temperature went up a lot more. So the temperature went up more because it's a different substance, or it's a different substance and the temperature went up more. Let's, by the way, look at this. That went up to 55 degrees, so it went up by 35.7 degrees. Let's make it a bigger block. Let's make it a block that's 10 grams of glass instead of 5, and now heat it. It had gone up to 55 degrees, but now it only goes up to 37 degrees. So the two things that matter, the temperature change, depends on what the substance is, it depends on how much heat, that is, how many joules of heat are you adding, and the mass of the substance. So those three things will be connected together. What the substance is, how much heat you're adding, and what the mass of the substance is. That's what's going to control, or that's what's going to relate to how much the temperature of the substance changes when it's heated. To do that, to look at the substance itself, we use a concept called specific heat capacity. And that is the thing that relates the relative amount of heat needed to heat different substances. And it's the energy required to raise the temperature of 1 gram of a sample by 1 degree. So if we look at our copper and our glass examples here, we didn't look at copper when we were doing our first thing, but if you take 150 joules and you add it to 5 grams of copper, it goes up by 97. It goes up by plus 77.9 degrees. If you do the same amount of heat to glass, it only goes up by 35.7 degrees. And what that means is that it's easier to heat up copper. It's harder to heat up glass. And what that means is it takes more energy to heat up glass by a degree than it is to heat up copper by a degree. So glass has the higher specific heat capacity. And copper has relatively low specific heat capacity. So the low specific heat capacity means it's easy to change its temperature. High specific heat capacity means it's hard to change its temperature. You can calculate specific heat capacity if you know how much energy is added to something. And it's basically specific heat is equal to the number of joules over the mass, that is the number of grams, times the change in temperature. So if you know those, you can just calculate the specific heat capacity. So let's do so for silver. If you add 150 joules to 5 grams of silver, the temperature goes from 20 degrees to 145 degrees. So the specific heat is equal to 150 joules divided by 5.0 grams times the temperature change, which is 125 degrees Celsius, because it went from 20 to 145. And if you calculate that out, it's 150 divided by 5 divided by 125, 0.24. And the units are joules per gram degree Celsius. By the way, you will also often see kelvins here, and that's the same value because we're talking about changes in temperature, and changes in temperature in degrees Celsius are the same as changes in temperature in kelvins. So the units for specific heat will sometimes be in joules per gram degree Celsius and sometimes be joules per gram Kelvin. All right. Now what we're going to do is we're going to take a short look at a table of specific heat capacities and just look at some trends. The most important is that metals have low specific heat capacities. Non-metal compounds, that is covalent compounds, tend to have high specific heat capacities. And something that's really important is liquid water has not the highest specific heat capacity, but a very high specific heat capacity, which has a lot of environmental and economic and societal importance associated with it, which is left for another day. All right. The key equation that you'll use for relating all temperature changes in substances is that the number of joules associated with a temperature change is equal to the specific heat capacity times the mass times the change in temperature. So this is the key equation for this area of our course. It's like the using molar mass or converting from liters to moles using molarity. It's the important equation to use here for temperature changes. So we can use this to calculate what the temperature change will be. We can rearrange the equation we just had for change in temperature and say, okay, well, if you add 324 joules of heat to a 24.5 gram iron bar that initially starts out at 20 degrees, what will the final temperature be? So to do that, we're going to need the specific heat capacity for iron. You get that from a table. It's 0.449 joules per gram degree. So the specific heat for iron equals 0.449 joules per gram degree Celsius. And therefore, the change in temperature is equal to the amount of heat added, 324 joules, over the mass, 24.5 grams, times the specific heat capacity, 0.449 joules per gram degree. And if you calculate that out, notice that joules cancel, grams cancel, and you're left with degrees Celsius. So 324 divided by 24.5 equals that, divided by 0.449. Our change in temperature is plus 29.5 degrees Celsius. The final temperature, therefore, is going to equal, this is a little hard to think about sometimes, so what you should do is make a little number line where you're starting at 20 degrees, and you know you're going up by 29.5 degrees, so our final temperature must be 49.5 degrees. That is 20 plus the 29.5. So that's our final temperature we'd have for iron for that. It's just that easy. Now let's go back to what happens to thermal heat energy. Remember, what can happen is it can be used to warm objects, it can be used to change phases, and it can be used to drive other reactions. And so what happens is when you have two objects come together, when you have a hot object and a cool object come together, when they meet, thermal energy is transferred. And what happens is energy goes from the hot object to the cool object. So the temperature of the hot object goes down, temperature of the cool object goes up. That thermal energy is transferred, and eventually what will happen is you'll reach thermal equilibrium. And what that means is the final temperatures are the same. That is, their temperatures will meet. The hot object will cool, and the cool object will heat until they reach the same temperature. When that happens, the heat associated with the warmer object is equal to the heat associated with the cooler object, but in the opposite direction. So one is gaining, one is losing, so the negative sign is there. But the amount of heat energy, the quantity of heat energy, is the same for how much the warm object loses and the cool object gains. So therefore, the specific heat times the mass times temperature change for the warm object, the hot object, is equal to the specific heat times the mass times temperature change for the cool object. When you do this, you have to use the numbers associated with each object, the hot object's specific heat, mass, and temperature change, and the cool object's specific heat, mass, and temperature change. There's a lot of kind of convention stuff you can do with this negative sign. My advice, just ignore it, make sure all these values are positive, and you'll end up with the right answer. So let's look at an example. If you have 5 grams of wood at 100 degrees, and you bring it into contact with 5 grams of copper at 0 degrees, the wood goes down to 82 degrees and the copper goes up to 82 degrees. And what that means is that the heat associated with the wood is going to be 100 degrees. It's going to be its specific heat, 1.8 joules per gram degree Celsius, times its mass, 5 grams, 5.0 grams, times its temperature change, which we're just going to use positive values for the magnitude temperature change, so that's 18 degrees Celsius. And if you look at how much energy that is, it's 1.8 times 5 times 18. That's 160 to 2 significant figures joules. If you look at the copper, it's a metal, so it has a relatively low specific heat capacity, so it's 0.385 joules per gram degree times 5.0 grams, because we have 5 grams of copper, times its temperature change, which is 82 degrees Celsius. And if you multiply that out, 82 times 0.385 times 5, you come out with, again, to 2 significant figures, 160 joules. So the heat energy to raise that Q, is equal to the heat energy to raise that Q. And we've reached this same temperature, so we're now at thermal equilibrium. And so that's what will happen. Whenever you bring objects of different temperatures together, the hot one essentially transfers heat to the cool one until their temperatures meet. You can use this in opposite to predict what the final temperature will be if you take the two things together. So let's look at taking 250 grams of water at 95 degrees and mixing that with 50 grams of water at 5 degrees. What will the final temperature be? Helps to do this if you draw a little diagram. So you have 50 grams of water at 5 degrees. And then you have 250 grams of water at 95 degrees. And so the cool water is going to go up, the warm water is going to go down, you're going to reach somewhere in the middle, and that'll be our temperature final, and we need to find that. So what that means is that our cool object will be 4.186 joules per gram degree, that's the specific heat for water, times 50 grams, times its change in temperature, which will be T final minus 5 degrees, 5.0, because that's our initial degree temperature there. That is going to equal 4.186 joules per gram degree, same specific heat because same substance, times 250 grams, times, now we have, starting at 95, we're going down to TF, so it's 95 minus TF. And those two values on either side will be the same. What's nice here is they have the same specific heat, so we can cancel that. And from here on out, it's algebra. So we have 50 times TF minus 5 equals 250 times 95 minus TF. And if you do this, it's going to be, we'll move the 50 over there, so TF minus 5 is equal, if we take 250 divided by 50, that's 5, times 95 minus TF. How much fun is this to watch? 95 times 5, that's TF minus 5 equals 475 TF. No. 475 TF minus 5 TF. No. I hate this part of the course. Not the course. I just don't like the algebra. It's just boring. And you can't do it fast, as I'm proving. So it's 495 minus 5 TF. So therefore, 500 equals 6 TF. So TF equals 500 divided by 6. 500 divided by 6, which equals 83.3 degrees Celsius. So that's our final temperature. So the key here was to get to this spot here. From there on was just algebra. And not much algebra either. All right. The last part of this is talking about what happens when it's not just heating a substance and having it get warmer, but when a change of state occurs. So you can warm an object, that's what we just did. The other thing you can do is you can cause a change of state. We'll talk about endothermic reactions later. The changes of states we're going to look at are going to be melting and freezing, which are the same thing in opposite directions, and boiling and condensing, which are in the opposite directions. And first, let's look at what happens. If you take some ice, and we're going to make what's called a heating curve, and so you take some ice and you heat it, and on the x-axis, we're putting how much heat you've added. On the y-axis, we're going to put what the temperature is as you're heating along. If you take some ice, it gets warmer. If it's at minus 50 degrees, it gets warmer until you reach 0 degrees, which is the melting point. And then what happens is the ice will stay the same temperature as you're heating it. And what's happening is the ice is converting from the solid to the liquid as you're adding this heat right here. Once all of it's melted, right at that point, it's all melted. Then you have just liquid water, and the heat now starts warming the liquid water. So that liquid water is warming until you reach 100 degrees, the boiling point for water. Then the heat is used to boil the water. And so as you're going along here, you're converting the liquid to the gas. At that point right there, it's all boiled. And now what you have is you now have gaseous water, and the heat is now used to warm that, and so now you're warming again. So what we're seeing is that when you have a single state, you warm things. When you're at the boiling or melting point, the heat is used to cause the phase change. And so there are two distinct different kinds of places where the heat ways the heat gets used. It gets used to warm a single state, or it gets used to convert between states. So when you're heating a single state, it's warming, and the kinetic energy is what is increasing. That is, the molecules are moving faster because you're heating them. When you're doing the phase changes, the temperature isn't changing, and because the temperature is not changing, the kinetic energy is not changing because the molecules aren't moving any faster, because that's what the kinetic energy measures. So in fact, what's happening is the chemical potential energy is increasing. And the idea is that delta H, the enthalpy change, is positive for melting and for boiling. The official word used for boiling is also called vaporizing. Okay, so let's look at this quantitatively. Oh, no, it's not. Let's first look at what's really happening. When you're warming, what's happening is the molecules are moving more rapidly, and therefore the kinetic energy is increasing. And the temperature increases because the temperature is proportional to the average kinetic energy. And so as you're heating up, the temperature is going up because the kinetic energy is going up. When you're boiling and melting, the molecules don't move more rapidly, and you know that because temperature is constant. And the temperature remains constant, as I just said. What's happening instead is you're breaking bonds between molecules, between one molecule and another. So you're not breaking molecules apart, you're just breaking molecules one away from another molecule. And so what's happening there is the potential energy, the chemical potential energy is increasing. That is, the enthalpy is increasing. And you could do this as an enthalpy diagram, as we did in the last section. So you can put enthalpy here going up, and you can put solid water there and liquid water there. And as you're heating, you're converting the solid to the liquid. That's melting on an enthalpy diagram. All right, so let's look at this quantitatively. Let's say we're going to talk about the changes of phase for water. What we need some number that associates how much energy it takes to do the melting or the freezing or the boiling or the condensing. And so the energy associated here and the energy associated here is associated with how much energy. What we need to know is how much energy it takes to do that phase change per amount of the water. And those energies are called the heat of fusion, is what we use for that. It's the enthalpy change for the fusion. Fusion means melting, which seems odd because you're not fusing something, but that's the way it is. And the enthalpy of vaporization, or the heat of vaporization, which is the enthalpy for boiling. And for water, it's different for different substances, but for water, it's 333 joules per gram to melt the water. It's 2,256 joules per gram for boiling. So it takes a lot more energy to boil the water than it does to melt it. Okay, so what we're going to do is we're going to do a problem, and the idea is to figure out how much energy does it take to do a bunch of different steps. And so we want to know if we have 40 grams of ice at minus 30 degrees Celsius, and we want to convert it to steam at 125 degrees, how much energy does that take? Whenever you're doing this is a heating curve kind of problem. Whenever you're doing this, the first thing to do is draw a heating curve. And the heating curves are always of the same shape. You have the solid heating, you have melting occurring, you have the liquid heating, you have the liquid boiling, and you have the gas heating. So that's the solid, that's the liquid, that's the gas, that's melting, and that's boiling. Those are always the same segments. And the key is to figure out where you start and where you end, so you can know which temperature changes to use and which phase changes to use, because you won't always use them all. So we know that for water, the melting point is 0, and we know that for boiling, for water, the boiling point is 100. And this is, in this particular case, degrees Celsius. So we're starting at minus 30, so we're starting down here at minus 30. And so our first phase is to go from minus 30 to 0. We know we're ending at 125. So we're ending at 125 degrees there. So we have 5 segments. We have warming the water from minus 30 to 0, melting it. The liquid will go from 0 up to 100. That's the heating of the liquid. Well, the boiling. And then the gas, the steam, is heated from 100 to 125. So we've got those 5 segments. We have this segment, and this segment. Those are the warming segments. They'll all use specific heat. And we have the melting and boiling point, and those will use the enthalpy change for fusion and for vaporization. So converting ice at minus 30 degrees to steam at 125 degrees, the first step is to warm the ice. So what you do is the specific heat for ice is 2.06 joules per gram degree. So it's going to be 30 grams. No, it's not. We're going to do 2.06 joules per gram degree times the mass, 40.0 grams, times temperature change, which is 30 degrees Celsius. And that's because we're going from 30 up to 0, up to the melting point. And so that, my friends, is 2.06 times 40 times 30. That is 2,472 joules. I said that with more drama than was appropriate. Next, we're going to melt that ice. That ice is going to get melted. And so the idea is, we're going to use, we have 40.0 grams times the heat of fusion for ice, which was 333 joules per gram. That's how much it takes to heat to melt 1 gram of ice. So 333 times 40, 13,320 joules for melting. So we've now done this part and that part. And next we're going to be looking at heating up the liquid. So now we're going to heat up our liquid. we're going to use the specific heat for liquid water, 4.184, joules per gram degree, or 4.18 in our listing here, gram degree Celsius, times 40.0 grams, times the temperature change. And now notice we're going from 0 degrees up to 100 degrees. And the reason you know that is from this chart that I'm harping about. You're going from the melting point to the boiling point. You won't always do that, but in this case you are. And so we have that times 100 degrees change. And so that's 4.18 times 16,720 joules. Okay, and now we have to, the water is all up to 100 degrees. We have to boil it. And so what we're going to do is we're going to boil it. It's going to be 40.0 grams of water times the enthalpy change for water, which is unfortunately 5 slides back. Where was it? 2,256 joules per gram. 2,256 joules per gram. That's the delta H of vaporization, the amount of energy it takes to boil the water. So that's going to be 40 times 2,256. 90,240 joules. That's a lot of joules. Most of the energy is right there. And the last step is to boil the water. Oh, that's what we just did. We just boiled the water. The last step is to warm the steam. And the specific heat for steam is 1.92 joules per gram degree Celsius. So you multiply that by our 40.0 grams times our temperature change. And our temperature change, remember, we're going up to 125 degrees. So the water is 100 degrees once it's boiled, and we have to go up to 125 degrees. So it's times 25 degrees. That's how much we're heating it by. And so that's 1.92 times 40 times 25, 1,920 joules. So the total is, we just add up those numbers. 1,920 joules plus 90,240 joules plus 2472. That's going to be annoying. 2472 joules plus 13,320 joules plus 16,720 joules. And so that total comes out to what that comes out to. Plus 90,240 plus 2472 plus 13320 plus 1672. Nothing better than watching me add, with a 0. No, I screwed up. I don't feel like doing this anymore. You add those up, you're college students, and that total is the total. And that is the end of this section.